Breakthroughs in modern data research tend to come from companies like Google, Facebook, and Amazon, with projects like MapReduce, Cassandra, and Dynamo. But 20 years ago, this type of breakthrough would be happening in academia, which causes today's guest, Peter Bailis, to ask, is the academic data community having an identity crisis? His exact words were, is the database community having an identity crisis? But this is what I translate his question to. Peter is an assistant professor at Stanford University, where he works on an analytic monitoring system called MacroBase. And our conversation explores MacroBase in addition to the discussion about whether the database community is having an identity crisis. And MacroBase lets us touch on the intrigue and the challenges of analyzing and storing IoT data, which he's working on with MacroBase. Peter also has some great YouTube talks about distributed systems. He's really a distributed systems expert, and he's a great public speaker, so I encourage you to check out those YouTube videos and definitely listen to this episode because it's an interesting conversation. Before we get to this episode, there's a few quick announcements. The Software Engineering Daily community has started working on a project called Software Daily, which was started by Jeff Tribble, a member of the community, and we're building an open source news and information site about software. I think this is an important project, and so if you're a web developer and you have experience with React.js or Flux architecture or Node.js or other software engineering web technologies, check out the repo. SoftwareDaily.com contains the repo. And pretty soon we'll throw up the website on SoftwareDaily.com. We'll start iterating on it even faster. And if you want to contribute to this podcast, SoftwareEngineeringDaily.com. Software Engineering Daily, sorry. You can go to SoftwareEngineeringDaily.com. You can find out how to become a host. You can contribute to the show. You can also find links to the Slack channel and my Twitter account. You can join the community Slack channel. And you can send me an email. You can also sign up for the Software Engineering Daily newsletter featuring the content that the Software Engineering Daily team is aggregating on a daily and weekly basis. I know that's a lot of information. So with that, let's get to this episode about Peter Bailis and the database community crisis. Everyone is talking about serverless architectures, and for good reason. It allows you to manage less infrastructure and deliver more results. At the forefront of this activity is the Serverless Framework, a popular open source application framework that makes it easy to build your serverless architecture on AWS, Microsoft, Google, and IBM. The team behind the framework has recently been funded by the investors behind Docker, New Relic, and HashiCorp, and they are looking for experienced, serverless-minded developers and evangelists to join them. If you have strong engineering experience with AWS Lambda, Elasticsearch, DynamoDB, and Redshift, or if you have experience building large, developer-focused communities, please go to serverless.com and apply. Let them know that you heard it from us, Software Engineering Daily. Thanks to Serverless for being a sponsor of Software Engineering Daily. We really appreciate it. And with that, let's get on with this episode of Software Engineering Daily. Peter Bailis is an assistant professor at Stanford University. Peter, welcome to Software Engineering Daily.
Thank you. I'm super excited to be here.
You gave a talk recently suggesting that the database community might have an identity crisis. What do you mean by that?
So I was on this panel where the title of the panel was, do we have an identity crisis? And I said, and this is for sort of a research audience, and I said, okay, sure. I think we might have an identity crisis in the sense that data is changing incredibly rapidly. The number of people who have to deal with data is growing every day, and large amounts of data, at that. And the way in which, at least conventionally, we think about data management systems is still a very narrow slice of what data means today, right? I think that data management goes much beyond storage or transactions. And the point of my sort of rant at this panel, which I wrote up and posted on my blog, was really just that we have a huge opportunity today to expand the role of data management and to really, at the end of the day, forget about the data management community or the systems community or the machine learning community, basically build better tools that can help people be more productive with the data that they have and that they're going to have in the future.
When you're talking about the database community and you're saying that they might have an identity crisis, are you referring specifically to the academic database community?
So in that particular talk, the audience was a bunch of database researchers from academia and industry at a great event that Google helped sponsor called the NorCal Database Day. So my audience for that talk was largely academic, but I think that if you look at the way in which database systems evolve, there's a very clear relationship between what gets done in industry at scale and what gets done in research. And so I think that the primary audience for that was, research, but I think that the lessons translate to industry as well. And I think the message, aside from the crisis bit, is really that today's data-intensive tools are kind of getting a very, very small piece of the pie, and I think we can do a lot better.
Okay, so let's unpack that. There's a couple things there. So one thing I think about is that many of the breakthroughs in the database community, they happen because a tech giant like Amazon or Google or Facebook has a problem that needs solving. With Amazon, we can talk about Dynamo. With Google, we could talk about Spanner or Bigtable. With Facebook, we could talk about Cassandra. And in each of these cases, there were specific problem sets that a company at the bleeding edge encountered and was enticed to create a solution that would meet that problem. Is there something about that pressure, the production level pressure, that causes these types of really important breakthroughs to happen?
I think that solving real problems is really important. And it's something that is very easy to do in industry, on one hand, because if you don't solve the real problems, you're out of a job or your startup tanks. I'd say that in academia, we have considerably more freedom. We can work on completely esoteric topics if we choose. But I think if you look at the most successful projects coming out of academia from the last several years, they were solving real problems, and they actually have begun to lead industry again. Systems like Spark, for instance, or Mesos, or some of my colleagues worked on Deep Dive, doing dark data extraction. And whereas in industry, there's a bottom line, there's a quarterly deadline, there are releases, there's a much more pressure to get the short-term thing working. That sort of ability to ease off the gas a little bit, pop your head up and look around the landscape and build something that's going to hit a need over the next several years, I think is becoming increasingly important.
When you talk about these systems like Spark or Mesos or Deep Dive, these are things that they did come out of academia, but at the same time, I could imagine them coming out of industry because they have very immediate practical applications, but yet they did come out of academia. So what was it about the atmosphere in these types of academic scenarios where they actually a real step change and a real important breakthrough was made? Was it something about the atmosphere, or was it just the people who happened to decide to be in academia that decided not to be in industry at that given moment?
I think it's definitely about the DNA of the people rather than the conditions, right? So you're not immediately incentivized as an academic to go after projects that actually have huge and immediate real-world impact like Spark, Mesos, and Deep Dive. But there's something about particular classes of academics like Matej Zaharia, who actually joining us at Stanford, Chris Ray, who's at Stanford, has been kind of leading the Info Lab for the last several years, who kind of something in their DNA makes them just want to solve real problems where there's a lot of research on these topics, parallel data flow, knowledge-based construction, and so on. But I think these guys have got it down where they say, well, gosh, we're going to try to find a real use case, right? So in the case of Spark, this was another Stanford professor who was at the time back at Berkeley, coming to Matei and saying, hey, my iterative MapReduce jobs are running really slow. And I'm trying to do this machine learning computation, but I have to write to disk every time I do an iteration. Matei said, let's see what we can build on top of Mesos to help make your job easier. And that's kind of where Spark came from. I think Deep Dive came from Chris Ray was an expert in these probabilistic databases and said, well, how can I apply these to real world problems? How can we take the amount of data that's sitting around? At the time he was at University of Madison, Wisconsin, and there were these people on campus with these huge sort of pools of dark data in the form of, say, PDFs about paleobiology. Now they've been looking at things like Craigslist ads for sex trafficking. And these researchers basically said, okay, I know something, right? I've got some tricks up my sleeve, and I want to see if they actually work in practice. And in my experience, and I think talking to my colleagues about this as well, who are trying to do similar things, the techniques that we have work, 80-90% of the time, right? They get you most of the way there in terms of getting the right abstractions or working. Actually, I don't know if I'd say the right abstractions. I'd say helping with the right approach to the problem. But when it comes to actually building something that works for a particular customer, and this doesn't have to be a customer, I use that term loosely, it doesn't have to be someone who's paying money, who's even in industry. This can be people like the paleobiologists that Chris helped out back at Madison to read the paleobiology literature, right? These can be people on campus, say in the med school, but basically having a customer or a user will require you as a researcher to push beyond what should work in theory, but doesn't work in practice. And I think it's that final, push from the huge amount of literature that's on these particular topics to a practical system where the best of systems research can be done.
And certainly you get the feedback loop out of having a customer rather than build something, write a paper about it, throw it over the wall, and then find it has all kinds of problems in terms of a production deployment. But the thing that I still have trouble wrapping my mind around is a company like Google, for example. Google has gradually adopted this enormous time horizon because they have so much cash in the bank. They have great cash cow businesses, so they can take really, really long time horizons in terms of the types of things that they invest in. They can throw money at all these different things. And in some sense, they have replicated the longer time horizon, the greater degree of freedom of the researchers who might want to come work at Google and build something that has no immediate practical application. But of course, those are the types of things that might potentially have enormous practical application because they're just something that nobody is even considering on the map. So I apologize if I'm harping on this too much, but I'm really trying to understand why a researcher would choose, and this is not like they should not choose. I genuinely am curious about why would a researcher choose to go to a research lab on a campus where they have a high degree of freedom versus going to Google where they might have an equally high degree of freedom?
Yeah, I think it's a great question. Honestly, I think what Google's doing in a number of spaces is really exciting. A lot of the projects out of Google X, TensorFlow, I think I even mentioned this in this talk that we started off just discussing, that I wish the database community had actually built a TensorFlow from the get-go. And I think that what Google is going to be very good at is essentially building out going from prototype to full-blown system, right? The fact that the students at Berkeley who are working on Caffe weren't able to build, the distributed version they weren't able to throw, by the virtue of the institution, hundreds of engineers behind the project like Google has been able to do, demonstrates the power of being at a place like Google. But I think that if you look at the types of results that are coming out of the top tier data management research groups, they really are still leading the field in the sense that, Google and Intel and a number of other companies that are working on, say, large-scale machine learning systems come by all of the time trying to figure out, okay, what are the latest results that they can start to put in their engines? So I'll give you one example. turns out when you're training these big, deep models online, it's very expensive to exchange all the parameters between servers synchronously. And so everyone for the past several years, starting back with some of Alex Smola's work at Yahoo, just basically runs these models in parallel and has all sorts of race conditions. And it turns out that in practice, these models tend to do fine, and they converge okay despite sort of a lack of synchronization. And for like probably at least 4 or 5 years now, people have been scratching their heads and saying, well, gosh, how much asynchrony is okay for me? How do I compensate for asynchrony? If I have a given model that's more dense or more sparse, how do I do this? And so that's a problem where industry was able to build a number of sort of world-class model training systems. Microsoft's Project Atom, Google TensorFlow, before that, Google Brain, Facebook has a version, Yahoo has a version, and no one knew how to actually address this sort of asynchrony term. And the academics didn't know either. But sort of after spending, I'd say 3-4 years working on this problem, one of the teams here recently had a major breakthrough. This is with postdoc Yannis Mitliakis and Chris Ray, that basically said, oh, we can model this in a very beautiful, elegant way. And they posted this result that says that essentially asynchrony can be thought of as having a term that acts like a fuzzy memory in your models. And you can actually tune for this fuzzy memory or this momentum term explicitly. And now Intel and Google and these guys are really excited about putting this in their thing. I mean, Yannis gave this talk at ICML a couple weeks ago, and he was swamped at this poster. Everyone was excited about this result where, again, they had the engineering. Well, they didn't have the conceptual framework for understanding how they should tune the systems that they had built. And that's a great example of this larger opportunity in academia where, look, aspiring to do Google class engineering in a research lab is a complete mistake. But looking for sort of conceptual breakthroughs like this asynchrony result or the algorithmic techniques that went into an engine like Deep Dive, or some of the insights that Matei had when he was building Spark, or the scheduling policies that went into Mesos. I mean, these are things that you can throw as many engineers as you want at this problem. And you need to throw many engineers in order to productionize these ideas. But ultimately, it comes down to thinking really, really hard and going really deep on a problem for several years until that sort of aha moment pops out. And I think that's kind of maybe, I don't know if it's, I think, what keeps me going, at least as a researcher, are those aha moments where it's not a matter of engineering time, but it's a matter of spending a lot of time in a space, trying to understand it, and then coming up with this moment of clarity where it says, okay, if we only do X, then we will solve this incredibly important systems challenge. And that doesn't come from just engineering.
And my sense is that the atmospheric sense that you get at a university simply is not the same as what you would have at a Google. For example, like if you're doing far-flung research at Google, the industrial elements of Google are going to pervade into your thinking. They're going to pervade your interactions. Whereas at a university, you're simply not going to have that noise. Maybe I'm wrong about that. I'm trying to empathize into a situation I have no insight into. But that's certainly my sense. I talk to my brother sometimes. My older brother does biology research, and he could certainly be doing it within industry. But my sense is that he really does want this freedom that is not just. It's not simply ephemeral. It really does have a pervasive effect on how your research proceeds and the degree of freedom and creativity you might have. And I don't know, maybe the sense of learning that is so pervasive in academia, because that is the whole idea of an academic institution.
Yeah, I really empathize with that in the sense that, look, everyone who's, especially at a place like Stanford, right? Everyone is here out of choice. And as a result of that choice, right, and the opportunity cost that, at least in the short term, that comes along with being in academia and not at one of, these large industrial engineering powerhouses, I think there is a very real sense that what we work on should matter. And what we work on should bring joy. And at least in my area of data management, I mean, I just think it's such an exciting time because the problems that we're working on, that we get to work on, that we get to choose to work on, are both in both spaces. They're in the space that says, okay, if we solve this problem, people will care, and we validate that by actually going out and talking to people. Right? We spend a lot of time pitching the work even before it's done to people in industry to see, okay, does this solve a real problem? But on the flip side, right? The other 95% of the time, we get to come back and scribble on the whiteboard and, stay up all night thinking about hard problems where it's not just for immediate or very high impact, real world impact, but it also sort of scratches this itch, this sort of curiosity that I think myself and a lot of my colleagues and certainly my students share. And it's sort of that shared sense of wonder and curiosity coupled with the leverage and the knowledge that if we solve the right problems, we can make a real difference. That makes the energy, at least around a place like this and in the Stanford Info Lab, really kind of infectious.
Mm-hmm. So talking more about this database identity crisis, we've touched on at this point the academic versus industrial notion that I have in a lot of these episodes, but you have some specific examples of how the database community has maybe missed out on some opportunities. And one set of examples you give is that the database community's ignored stuff like NoSQL and big data because these things do not fit the traditional relational model of database systems. But you also point out that before the 1970s, the relational model was not actually the norm. As an example of the problematic ossification of the database community, why did the relational model stay prominent for so long as to make the community ossified for how this is the way databases work?
Yeah. So the question is, why was the relational model so revolutionary and then now it's kind of holding us back? Is that the type of thing you're getting at? Or?
And more, why is this iconic of the types of stubbornness or ossification that we could have in the community at large?
Right. So I think there are a bunch of factors that come into play when new technologies come in, right? So I'm fully aware that many ideas from data management, I'm not aware. I really believe that many of the core ideas that the data management community has developed over the past several decades, things like declarative languages when you want them, things like the relational model when you want it, things like transaction processing when you want transactions, are actually a good idea. Okay, and I think that in a sense, the success of the database research community is borne out by the massive industrial impact that it's had, by the fact that almost every major business process today has a relational database somewhere in it. The challenge that I see for our community is that in spite of these successes, changing applications and also changes in hardware more recently are forcing people who have real problems in practice to seek alternative solutions. For instance, when I think about NoSQL, I think about the fact that web developers don't want to declare their schema up front. I think about the fact that transactions can be prohibitively expensive in a distributed environment. And the way this bears out in practice is that people start to build tools that solve the problems that their existing tools and systems in the ecosystem don't solve. So in the case of NoSQL, people wanted to have easier to use databases. So they didn't have to declare a schema. So they built, MongoDB and Riak and Cassandra. And my sort of the tension that I see in the community, which is what my talk sort of spoke to, was this idea that yes, the relational model has been hugely successful. And no, we don't have to throw it out wholesale. The systems that we've built contain valuable concepts and abstractions. But on the other hand, we should also be cognizant of the fact that the way in which people are using data, in the case of, say, NoSQL, they don't want to declare their schemas anymore, or at least at the start of their application, means that we should maybe consider paying attention a little bit more. And I think that, part of my rant was somewhat of a reaction to at least some of the more senior members of the database community's original responses to things like NoSQL and MapReduce, where rightfully so, people like Mike Stonebraker pointed out that in fact, parallel data flow engines had been invented in the 1980s, and there were many concepts that database engines had provided that really did solve, would have solved several of the problems, at least in theory, that the authors of MapReduce were grappling with.
Yeah,
but on the other hand, though, it's not like it's not like any existing relational database could have solved Google's problem either. So I think it's more of a yes and than a no but, right?
Yes. Yeah. I think the Stonebraker example is interesting because I think he's a luminary in the database community and has done so much innovative work. But his initial response, his now famous initial response to I think it was the MapReduce stuff was pretty critical and kind of because he may have been missing some things like you pointed out. So given that the database community is having this identity crisis, you have some suggestions for what to do about it. A quote from you is, "I believe our role as a community is to discover and define the future standards for how data-intensive platforms and tools should look and operate." What are the ways that the database community can accomplish that goal of discovering and defining the future standards?
Yeah, I think there's this guy Le Corbusier who's this famous modernist architect, and at the time he was doing these crazy designs where people said, "Oh, this doesn't look anything like the buildings that we're building." But in fact, after sort of repeated trials and sort of pushing into new parts of the design space, Le Corbusier basically invented a lot of, or was very influential in sort of leading people towards a more modern conception of what architecture looked like, and Le Corbusier says something which I really believe in myself, and I think is a great answer to your question: how should we actually establish new standards? And Le Corbusier says, well, a standard is definitely established by experiment, right? So by trying out a number of different designs, by pushing boldly into new application areas or new forms through which we can construct, say, data management tools, we can start to understand what the new standard should look like. And I think it's not a top-down process by any stretch, right? I think that the way in which, for instance, the data management community can experiment is by building systems that don't look much like anything people have built before. They don't necessarily have a relational interface, or if they do, they provide analytics functionality that no existing engine has provided, and see what sticks, right? So this is our prerogative as researchers. We can essentially afford to experiment. It's our job to experiment. And my hope for the community is that we take big risks. We take big chances. We throw a bunch of stuff at the wall and see what sticks.
If you want to learn about Kubernetes, go to apprenda.com/sedaily. Today, you can find a webinar about Kubernetes covering microservices, persistence, and multiple clusters. You can also find links to a past webinar covering the history, the origins, and the technical architecture of Kubernetes. The webinars at apprenda.com/sedaily are hosted by Joseph Jacks, a member of the Cloud Native Computing Foundation who was previously a guest on Software Engineering Daily. If you're looking to move to a cloud-native infrastructure platform that works with your existing apps, you should also check out apprenda.com/sedaily. Apprenda provides cloud platform software that works with your existing applications and infrastructure. So if you're looking to migrate to cloud native, but you want to maintain your existing applications, you might want to check out Kubernetes and Apprenda. Thanks to Apprenda for being a sponsor of Software Engineering Daily. And if you want to learn about Kubernetes while supporting Software Engineering Daily, go to apprenda.com/sedaily. That's apprenda.com/sedaily. Thanks again, Apprenda. bold, weird, and hard projects are what you suggest academics should pursue. So if I'm entering my graduate studies and I want to do some research in the database community, how can I find a project that will satisfy these bold, weird, and hard requirements?
Yeah, I think there are sort of at least two things that come to mind. The first thing I would say is find a real problem to work on. Even Mike Stonebraker will tell you this, right? If you ask him, Mike, how did you get the idea to build a new column-oriented data warehouse? So, I was talking to people who were managing their warehouses, and he noticed they have really, really, really wide rows. There's a bunch of columns in those things. They don't touch most of them, right? Simple observation that was informed by practice and yet led to this huge amount of research, really exciting research on how to actually build an engine around this simple observation that people have these wide rows. So number one thing, find a real problem. And this doesn't have to be a problem in industry, right? Go to the med school, go to the humanities department. I mean, digital humanities is incredibly exciting. Go to chemistry or biology, ask people their data management problems and say, what's hard? And the second thing that I would say is be creative, right? I think that the new forms of data management tools, will probably have the future of data management in 10 years. It'll probably still have a relational interface somewhere, but the types of functionality and the types of queries people want to perform are probably going to look radically different than just standard relational operations. So a specific example of this is my colleague Chris Ray's work on data programming has made it so we can basically just input very simple rules about data, about relationships between data. They don't even have to be right all of the time. And the engine is geared to understand these rules that are expressed in a very high level language and perform very powerful statistical inference in order to determine which facts in the database are more or less likely to be true. Okay, so this is a completely different way of programming. It's saying there's no, there's a table, but there's no SQL, there's no transactions here. It's literally just explaining facts about the world that say things like, if two people appear in a sentence and the word wedding appears in the sentence, the two people might be married, right? You give the system enough of these things, and then it starts telling you things like, okay, Barack and Michelle Obama are definitely married. That's like a totally different interface than what you get from a database like Postgres today. By the way, deep dives built on top of these databases. So I'm not suggesting we throw them away, but I'm saying, if we're bold and if we're seeking out these bold and weird ideas, we need to be a little creative about what the interfaces should be doing. And I think, one rule of thumb here is that I strongly believe that sort of form should follow function. So if you have the first thing, which is the user who wants to use your tool, or could possibly become a customer of a prototype that you build. And a prototype doesn't have to take more than a couple weeks of engineering if you do it right. Then you can start to explore these design spaces, which look radically different. It will push you in all levels of sort of the data management stack in different directions than you might have otherwise if you decided to sit down and write a thesis on buffer pool reclamation policy.
The deep dive is definitely a topic I need to do a show on. With deep dive as an example, how do we know when one of these new data technologies has been successful enough to warrant wide adoption? Like, so deep dive, for example, it's like you said, it's kind of a totally different experience than a traditional database, or most of the things. Actually, I honestly don't know much about it, so maybe I'm just speaking off the cuff here. But if I'm a software engineer, I would have trouble imagining, like, what is the scenario where I'm going to use deep dive. So I don't know, how does the chasm get crossed between something like deep dive being researched and developed as a prototype, and when can it cross the chasm into actually being, the kernel of a production grade system?
Yeah, it's a great question, and it's one that we struggle with a lot in research. Right, it takes a lot of, we wear many hats when we do this style of research. we're simultaneously trying to validate use cases. We're trying to solve the problems that have arisen in the previous use cases, and trying to figure out what's next on the horizon. Okay, like what should we be building for the next couple of years out. And I think that at least the way that we do things in the info lab here is we spend a lot of time establishing who's sort of what would be like the sort of key use case that we're interested in addressing, right? So for Chris, when they were building Deep Dive, their big challenge was trying to match the quality of a human-generated sort of people decades worth of work paleobiology database, which basically contained not all the facts, but let's say many of the facts it contained a large collection of facts that we had accrued over the years in thousands of papers about the fossil record. And they said, okay, if we can build an engine that can automatically scrape these PDFs and extract similar quality, if not better quality, results to these, to the human curated database, then we think this will be a good jumping off point to going to these other domains in which they're operating now. Places like biology, places like this sex trafficking work they've been doing. And I think that now, folks from industry have started to pick this up as well. And so I think, in terms of evolution, I think about it as what are the killer sort of use cases, and what is the one challenge problem you want to solve, that once you solve that challenge problem, you have a sense that this is going to be, it's going to be a jumping off point where the core ideas, even if they're not entirely worked out, will at least stabilize enough where people in production can start to pick this up.
So you bake the project around a reasonable base case such that the induction step can happen quite fluidly if you solve the base case.
Absolutely, yeah. And it doesn't have to be, yeah, exactly. Or alternatively, if the base case is not well defined, there's an opportunity for rapid iteration. In my group, we've been building a new analytics engine around what we're calling analytic monitoring for large-scale machine-generated data, or if you like to call it, Internet of Things data. And for this particular project, this engine we're calling MacroBase, we literally started off for a couple months last fall reading the stats literature and trying out a number of sort of very simple prototypes. And by prototypes here, I really mean even things as simple as Python scripts over a particular telematics application whose sort of operator was in Cambridge, down the street from the lab in which I was working, right? So like it was literally saying, well, this guy has this organization doesn't have a great sense of what's going on in their data because there's too many, Android devices. They have many, versions of their app, and there's many different versions of the OS. And we want to know, can we pick out interesting combinations here? Okay, so it's like just sitting down with these guys and saying, okay, that sounds like a cool problem. Let's see what's the dumbest thing we can try, and then iterating quickly in order to sort of get those lessons where we can start to build a real prototype around something.
You're talking now about MacroBase, and I did want to ask you about this. So this is an analytic monitoring system for the Internet of Things. What are the canonical challenges with storing and analyzing this type of IoT data?
So I think there are really three major challenges in reasoning out this data. The first one is that this is just really, really big data. And I mean this
and fast.
In a literal sense. Yes, exactly. So, a lot of big data, you can still fit on a machine with a terabyte of RAM and you're done. Machine-generated data just keeps coming. And this means we need to have not just scalable systems, but we also need to build systems that help humans understand what parts of the data should look at. It's just not feasible to inspect every record, right? And what's so funny is that sort of big data and the confluence of cheap storage and pretty good I would say better ETL pipelines and data loading pipelines than we've had in the past mean that people have all this data sitting around and it continues to grow. I mean, both LinkedIn and Twitter have talked about the fact they're ingesting over 14 million metrics per second from their production infrastructure. And there's just like no chance that a human can look at that. When you couple that with the fact that a lot of the behaviors in these streams occur on the order of seconds or minutes. So you don't want to do offline analysis. And also the fact that because you're gathering data from a variety of sensors and devices, that sort of combinatorial explosion means you can't just look at the data and say, oh, okay, Android version, Android Cupcake running on the Galaxy S5 and our app version 0.3.2, oh, that's clearly where the problem is, right? It's too hard for humans to look at this. And so our sort of main thesis here is that this combination of scale, the demands for timeliness, and the sort of heterogeneity of devices is going to necessitate the development of new data systems infrastructure, which is where MacroBase comes in.
And what are the architectural principles around solving those three problems?
Yeah, so there's sort of two main focuses in the project. The first of which is that, at least from the statistics and machine learning literature's perspective, there's a lot of solutions to the problem of detecting strange things in data and then starting to summarize them. And we call these sort of anomaly detection and explanation. So they're somewhat classic problems. But on the other hand, from the systems perspective, you say, how do I build an engine that can handle millions of events per second? And suddenly you're back to square zero, where you have kind of the right blueprint for the types of techniques you might be looking at, but actually coming with the right operators that enable you to scale accurately to these high data volumes is really a huge area of focus for us, where we try the basic stuff out. It takes can process maybe 1,000, maybe 10,000 events per second, which is nowhere near the scale in which we need to be at, especially if we want to enable sort of interactive exploration. But then sort of more architecturally, we've really tried to go down a kind of radical path here, which is, if you think about MongoDB, the system took off because it was so easy to use relative to setting up any sort of relational engine. And I and many of my colleagues actually at Stanford believe that we're sort of in a similar situation with advanced analytics tools, right? It's way too hard for the domain expert who knows about their application, who knows about things like the wind turbines running on their wind farm, but isn't necessarily an expert in distributed data flow or isn't an expert in machine learning. Getting them productive in an engine like MacroBase is really challenging. And so we've really built this engine for what we're calling sort of pay-as-you-go functionality, where out of the box, you can just select attributes of your data stored in whatever database you're using, and you'll get results. And then if you want to run more sophisticated analyses, you can start to configure your data flow pipelines yourself. And so that's been a really interesting sort of challenge, but also an opportunity in the sense that we have an engine. It's not particularly well documented. We're going to be putting some more time into documentation in the next couple months. But where, probably at least once or twice a week, I get emails from people at very exciting organizations who say, hey, I downloaded the tool. I'm running it on this data. Here's what I'm finding. Or alternatively, sometimes it's, why isn't my database connection working? Or, it's a little bit of troubleshooting. But basically, we've built this engine in a way where out of the door, out of the box, you can get something useful via kind of a default pipeline. And then as we do more sophisticated, as you want to do more sophisticated analyses, you can actually get under the hood and start to play around with the data flow in ways that sort of conventional analytic systems wouldn't let you do or be very difficult to do today.
How does MacroBase contrast with the way that these other IoT solutions are approaching the problem? I don't know if you've looked at the Amazon IoT platform or Google's or Azure's.
Yeah. So at a high level, what we're really shooting for is something that okay. I think this comes down to, actually, yeah. So I think this comes down to something you brought up earlier, which is, where do you decide to put your time in research, and what types of tools do you build in a research scenario? And so what I see in the market today is a large number of people who have recognized the potential of IoT, and in many cases, we're still building what I would call maybe the plumbing for building a real IoT application, right? So many IoT platforms are all about things like data collection and aggregation, shipping them back to a centralized server, registration, naming, kind of all the things required in order to suck that data up into a data lake or a centralized location. And that's super important. In fact, I think it's necessary. But that sort of plumbing I think of as the first level in what we might call the IoT hierarchy of needs. So you go from plumbing. Once you have the data, you want to know, okay, so once we solve the plumbing problem, we have the data, what do we do with it? And that's where MacroBase is designed to come in. Once I have a pipeline that's starting to ingest the data from my devices, what should I look at? Because if I'm at scale, as an increasing number of domains are, I can't look at all the data. I have no idea where to prioritize my attention. And so compared to a lot of offerings I see in the market around IoT, we're really shooting for a higher level functionality, which is kind of this analytic monitoring or understanding component. And I think that's one of the luxuries we have in academia, and that I don't have to worry about the pipelines. In fact, I would not compete head to head with Google or Amazon on this plumbing step. But I do believe that once we have all of this data, making sense of it is going to be increasingly important. And sort of for the early adopters of many of these sort of IoT techniques, or I'd say for early adopters of IoT or people who have IoT applications who have hit the second step, there's really not much in the market that helps them at this point. And yeah.
So typical IoT pipeline in production today might be, I've got a ton of events coming off of my thermostats in a warehouse, and those are all hitting a Kafka queue, and that's getting ingested and written to Cassandra, and then Cassandra or somewhere in my pipeline, I'm detecting where the temperature is too high, and I might use my IoT infrastructure to signal back to the warehouse, hey, turn on the AC or do something. And it sounds like MacroBase is at that layer of where you're processing over the data that you've already ingested and already stored, and you're maybe doing better detection of the types of scenarios where the temperature is too high.
Exactly. Yeah. I mean, I think that if you look at what people do for monitoring today in these scenarios, you kind of fall into one of two camps. On the one hand, you have a lot of techniques. You can deploy static rules. And in fact, like a shocking number of people who do this stuff very, very high scale today, especially in I don't know if this is IoT, but I do think it's an interesting source of machine generated data. If you look at data center monitoring, it's largely kind of static alerting, which works relatively well. But what this does is it sort of misses the potential to detect events that are significant, but not necessarily critical. So if, for instance, I could, instead of just getting paged when one of my servers is down, I could get a report saying, hey, by the way, this make and model of processor, or this rack, or this host is behaving abnormally, right? Maybe this processor is behaving much better than the others in the system, so you should buy more of it. Maybe this container is on the fritz, and its network card is having difficulty, and I'm seeing queuing delays, right? These sorts of like degradations, but not critical failures, essentially lead to a lot of efficiency loss, at least that we've seen in practice. And I think that static rules don't catch that. On the opposite end of the spectrum, right, you have people who do this for a living, this type of sort of alerting and sort of, I just call it alerting and monitoring very, very well. Like, Visa has a team of 200 plus people, working on fraud detection, and they do a pretty good job of it. I think I'm sure they'd be interested in improving this, but it's like a core focus and a core part of their business. And I think the gap that we're interested in bridging is essentially, on the one hand, people who need to have scalable alerting rules, but on the other hand, So the gap is really between these really simple alerting rules and more advanced functionality. And getting that more advanced functionality without compromising on scale, without compromising on accuracy, and without having a 200-person engineering team behind it is really where the opportunity lies.
So can you talk a little bit more about how MacroBase works? I mean, I've got all this data, it's being ingested, it's being stored. What am I doing with MacroBase in a little more granularity?
Absolutely. Yeah. So we've been looking at a couple different domains. One that I can talk about probably more extensively is mobile application monitoring. So we worked with this telematics company. They sell called Cambridge Mobile Telematics. They sell a wonderful application. It will help provide feedback on your driving experience. So they'll tell you, are you braking too much? Are you accelerating too much? They'll give you sort of suggestions for how you might improve your driving to become a safer driver. And as a result, in order to provide this functionality, they deploy a bunch of really interesting sort of sensing and complex modeling on the phone and also in their data centers in order to sort of provide these recommendations. So when we deployed MacroBase over CMT's data, what we did is we basically sat down with them and said, okay, what are the key application metrics that you care about in the CMT application? They said things like, well, we want to make sure we're not causing too much battery drain. We want to make sure that we aren't seeing sort of abnormally short trip times, which might indicate a problem with the trip detector running on the mobile phone. We sort of sat down and said, what are your key application performance metrics? And then, using the MacroBase UI, we can basically highlight these graphically and say, okay, in this database, these are the things that we care about. These are where we want to look for sort of anomalous behavior. And instead of just reporting all the points we thought were anomalous, right? These guys have, a very, very large number of users running a bunch of different phones, different versions of the app. We asked, well, okay, how would you like us to summarize or what sort of metric or what sort of attributes about your data would you like to see in a report? And they said, okay, well, we want to know if it's particular phone types that are like device types that are causing problems. We don't know if there are particular versions of the OS that are causing problems. We don't know if there are particular versions of the app that are causing problems, or alternatively, leading to improved behavior. Right? It's not just about finding the faults. So again, in the UI, you highlight, okay, these are the attributes I'm looking for explanations for, and we kick off a query in the backend. There's a UI that you can use this. There's also sort of configuration files that'll enable you to do this, and the system reports sort of interesting combinations of attributes that help explain what might be going on. So in one case, we found that a particular model of phone and a particular OS version were having difficulty or were correlated with high power drain. We said, oh, there might be something going on here. I think there's a few things that we've put in a paper on the archive. I'm trying to remember which things we put in there, but basically, based on these key performance metrics and these attributes, we basically find the combinations of attributes that help explain what's going on. And the level of functionality, at least out of the box, is as simple as just selecting your performance indicators, your attributes, clicking a button, and then the system will provide a list of combinations, like this version of OS, this version of the application were abnormally high. Here's a histogram of what the overall population looks like and what the subgroup looks like. And if you want to, you can go back to the database and pull out those rows and sort of start your root cause analysis from there, where you're highlighting a very small set of combinations from the explosion of combinations you might otherwise consider.
Okay, just to begin to wrap up, so I find this IoT space to be so interesting, and given that you have been examining it under something of a microscope, what are the problems, the challenges that are at the fringes of IoT that you did not realize until you started examining it with that microscope? The things where you're saying, oh my goodness, this is going to be a problem that we're going to be grappling with for the next decade.
Yeah, I think that, so it's very funny, but I think that sort of IoT's biggest challenge is also its biggest strength, okay? So the challenge in IoT from the data management perspective that I see is this scale in terms of volume, so raw events per second, and heterogeneity of device types and of reading types and of sensor types, okay? What's really fascinating about this is that under the microscope, we've started to recognize that this scale actually helps the type of analyses we might perform. So simple example, if you're trying to detect credit card fraud, you need to detect the one guy who swipes your card at the ATM for $2 at the gas station. Or if you're trying to detect, do network intrusion detection, you're looking for the one attacker who logs in via SSH once and copies the files off the server. These are really, really hard to detect. And there's also not as much data. It's about credit card transactions. There aren't as many compared to what the data coming off of, say, a production data center looks like. What's fascinating about this is that because there is so much data coming off of IoT devices, the interesting behaviors that we'd like to find appear in mass. Right? We're not looking for the needle in the haystack anymore. It's still sometimes useful to try to find that. But because there's so much data, if we can meaningfully process it, we can actually improve the quality of the results we provide in an analytics engine like MacroBase. We can not only get better sort of understanding of the large-scale trends in data, but we can actually deliver sort of more statistically significant results as well, because instead of processing thousands of records, we process millions. And it's fascinating to see, for instance, the statistical techniques that people just really struggle with in something like a clinical biology setting, where you have 1,000 patients with 1,000 different outcomes. And you want to know, did this drug help or not? Or which combination of lifestyle factors affected someone's survival rate? And in that setting, the sample size is so small, it's very hard to draw meaningful inferences in the sense that the significance is hard to achieve. Whereas in IoT, when events do occur, provided we can process them at scale, we can be very confident that there is in fact an underlying systemic behavior. And I think that sort of treating this greatest challenge in IoT as a strength in analysis, as a strength in helping people understand what's actually going on in their data is extremely exciting, at least on the research side.
Okay, Peter. Well, this has been a treat. I really enjoy your YouTube videos. I watched one just last night, one from MesosConf, I think, where you were talking about the basically distributed coordination among systems that don't have to be synchronous. So I recommend people check out Peter's YouTube videos and his blog. And Peter, thanks for coming on the show. This has been a great conversation.
Absolutely. Yeah, thanks for having me. And if listeners find this stuff interesting or are excited about learning more, talking more, say, hey, this guy doesn't know anything about IoT. My IoT problem looks like this. I would love to hear about it, because at the end of the day, the work we do and the work many of my colleagues do in the Info Lab at Stanford is informed by real problems we sort of hear about from not just going and talking at conferences, but hanging out in the hallway track, or getting random emails from people, or people trying out a tool and saying, this thing is great, or this thing sucks, or you should work on this problem instead. And so, feedback along those lines would be great. And just in general, I really appreciate the opportunity to come on, because at least for me, practice very much informs my research agenda, and I'm incredibly excited about I think, hopefully, as you can tell, about what practical demands for data management mean for database systems research.
Okay, well, send your IoT questions to Peter Bailis. Thanks for coming on the show, Peter.
Yep, thanks.
Thanks to Symfano for sponsoring Software Engineering Daily. Symfano is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symfano.com/sedaily. That's SYMPHONO.com/sedaily. Thanks again, Symfano.